Welcome to Real-World gRPC with ASP.NET. In this video, we'll talk about the different ways we can maintain our gRPC contracts. When using gRPC for service-to-service communication in a distributed system, it is important to find a way to manage the protobuf contracts in a way that is convenient to use for the developers, provides a clear way for authoring and reviewing changes and contract versions, and fits into our CI/CD infrastructure to easily compile the contracts and generate client libraries on every change. This is a topic I have not seen being discussed in most beginner tutorials, yet I think it is very important in order to achieve a convenient and efficient developer experience when using gRPC for service-to-service communication, especially in an infrastructure using multiple different technical stacks. In this video, we'll see 3 different approaches to maintain the contracts. This overview is by no means complete. There are other possible solutions as well. But these should give some ideas about the possibilities, which we then have to fit to what works well for our organization's infrastructure and service landscape, depending on how our services are structured, whether we have a monolithic or a distributed architecture, how diverse our technical stacks are, and how our CI/CD system is set up. The first approach we'll look at is storing the proto contract files in the folder of our ASP.NET project and referencing them in the project directly. In the second solution, the contract files are maintained in a dedicated repository, which is included in the service repo as a Git submodule, and the proto files are still directly referenced by our service project. And the last approach is implementing all the proto compilation and client library generation separately as part of the repository containing the contracts, which outputs Nuget packages that our services can reference instead of using the contract files directly. The first approach is arguably the simplest, and it is what is most often included in beginner tutorials for using gRPC with ASP.NET, where the proto contract files are directly included in the ASP.NET project, and they need to be duplicated in the repository of every application requiring the contracts. The diagram shows this setup for a service called customer service implemented in ASP.NET, which is used by another service called email service implemented in Python. In order to be able to send the gRPC calls, the Python service also needs the same contract files to be able to create the client objects. We also used this approach in the example in the previous video, where we had one single proto file. Let's see a more realistic example. In a real-life system, our contracts would typically not be in one single file, but rather we would have a gRPC module with multiple packages to structure our contracts into domains, like how we structure our C# code base into projects. The contracts define a service called customer service with one RPC for retrieving a customer specified with an identifier. The contract is split into 2 proto files in 2 separate packages. The file customerservice.proto contains the service and the RPC getCustomer for retrieving a customer record. The other customer model proto file defines the customer data type. This example, of course, is much simpler than the contracts of a real production system, but by having multiple packages referencing each other in a folder structure following the protobuf conventions, it can already illustrate how the contracts would be set up in a more complicated system. While technically optional, it is good practice to organize the contracts into packages by adding the package specifier to all of our proto files. The convention when creating protobuf contracts is that the folder structure should follow the package names exactly. And the name of every package should end with a version number, which is useful in the case of having to introduce breaking changes. When importing a proto file, we need to specify the full path to the file starting from a folder which is considered the root of the protobuf module. In this example, that is the protos folder in our project, from which the folder structure of the protobuf packages starts with the My Company folder, which is also the first segment of the package names. When using multiple proto files importing each other, various tooling might need some extra configuration to use the right root folder for the protobuf module. For example, in Visual Studio Code, the proto3 extension by default considers the root of the opened folder the root of the protobuf module, from which the imports are evaluated. Which doesn't work because our protobuf module is rooted in the protos folder of our .NET project and not at the root of the solution folder which is opened in VS Code. We can fix this by configuring an extra input flag for proto-C in the VS Code settings, and because this setting is specific to this particular repository, it should be configured in the repository-specific config file and not in the default VS Code config. With this flag, we specify the root folder of the protobuf modules from which the imports are interpreted. In order for the models to be generated in our project, we need to add the protobuf reference to all of the contract files. Once we add the references and try building our project, we will get build errors similar to the linting errors we got in VS Code. This is because the configuration we did just now works for the proto3 extension, but the .NET gRPC tooling also needs to be configured to know about the correct root folder. This can be done by adding the additional import dirs attribute to the protobuf element in our project file. Once it's added, the project successfully compiles and the data models and the client and server stubs are generated during the build. This simple approach of directly adding the proto files to our .NET project is what's shown in most beginner tutorials, and it's suitable for a Hello World example, but I don't think it's sufficient for a real production system due to the following reasons. It does not provide a way to reference the contracts in other services, as the contract files are embedded in our .NET project. And changes to the contracts and changes to our application are mixed together in the same repository. There is no way to review and version changes to the contracts separately. In a more complicated production application, where we want to use the gRPC contracts for service-to-service communication between distributed services, especially if they use different technical stacks, it would be preferable to extract the contracts to a separate repository that our services then can reference or import in some way. This brings us to the second approach, extracting the contracts to a dedicated separate repository, which we call customer-service.contracts on this diagram. This repository can be included as a Git submodule in every application repository which needs the contracts. To illustrate this, I have uploaded the contracts we used in the previous example to a separate dedicated Git repository. This is what we will add as a submodule to the repo containing our ASP.NET application. We can do this with the git submodule add command. After executing the command, the contracts repository will be cloned inside the repository containing our service. Then we can reference the proto files in our .NET project the same way we did before, with the only difference that the files reside at the root of our repository, so we need a different relative path both to specify the location of the files and for the additional import dirs attribute. This approach has the benefit that the contracts are now extracted to a separate repository and can be imported and referenced in every service that needs them. The drawback is that the necessary setup for generating the client libraries will be repeated in every application repository. For .NET, that's not too complicated, as it only requires adding the gRPC tools package and referencing the proto files in our project. But in case of a more complicated module containing more contract files, this can already result in quite a lot of lines of boilerplate code. And in other technical stacks, it might be even more involved. And the other issue is that not every developer is familiar with using Git submodules, and this approach also doesn't provide a nice way to do versioning, because the submodule cannot be checked out at a specific Git tag. although it can be set to a branch, so we could still do versioning by creating a branch in the contract repository for every published version. The third approach solves these problems by not just extracting the contract files to a dedicated repository, but also setting up a build process to generate the client libraries for the desired technical stacks and publish them as packages with the respective package managers like Nuget for .NET, npm for JavaScript, or pip for Python. The various services can import or reference the package for their respective technical stack, thereby having access to the server and client stubs generated from the contracts without needing to have the underlying proto contract files. This example shows how the library generation can be set up for .NET. To illustrate this, we'll use the same protobuf module as before with two proto files. The protobuf module is at the root of the repository, in which I also created a folder called code generation to contain all the further necessary content to generate the libraries. Here I added a .NET folder with two class library projects in which we will generate the models and stubs and publish them as Nuget packages. Technically, it would not be necessary to create two separate packages. We could include all the contracts in one single project and Nuget package. But for the sake of consistency, it's a good idea to create one package for each protobuf package. This way there will be a nice symmetry between the protobuf and Nuget packages. And it also has the benefit of being able to reference only the packages we really need. For example, if a service would need to directly serialize objects using the protobuf models, but not implement the gRPC service, then we could reference only the model Nuget package and not the one containing the service stubs. These projects can be completely empty because all the code will be generated during the build. And the project setup needed is the same we used before. We need to add the necessary Nuget packages and the protobuf reference using the correct relative path. And in the project for the service contract, which depends on the model contract, we can add a reference to the other project, which will be correctly translated to dependencies between the Nuget packages when the projects are pegged. And if we would like to implement some extra extensions to the generated models, that can also be easily done with this approach by adding some handwritten C# code to the library project, which will also become part of the published Nuget package. And because the .NET tooling creates partial classes for all the protobuf message types, we can even directly extend the types with additional properties and methods. Let's say we would like to add an extra property to the customer type, which returns the full name of the customer. We can do that by creating a partial class definition using the correct namespace and type name and implementing the additional property. This way, all the consumers of the Nuget package will be able to utilize this extra capability. To create the Nuget packages, we can issue the .NET pack command in the solution folder. Once it's done, the package files will be generated in the bin folder, which we can upload to our Nuget repository. Once the Nuget package is published, we can use it in all of our service applications, and we don't have to add references to the protobuf contract files anymore. You can see it in action in this project, where we are referencing the published Nuget package. And in the implementation of the service, you can see that now the base type is not coming from the types generated in this project at build time, but rather it is coming from the Nuget package. And the implementation also illustrates how we can use the extra full name property we implemented as an extension in the package. Once we have this set up, we can add the contract repository to our CI/CD system to make sure the Nuget package is built and published on every commit. Depending on the capabilities of the CI/CD system we are using, it's also a good idea to publish pre-release versions from every commit on a non-main branch and publish stable versions from the main branch. And in addition to doing the .NET build and Nuget publishing, we could introduce similar setups here for other technical stacks like TypeScript, Python, Java, etc., and wire all of them into our CI/CD pipeline and make sure to publish packages with consistent version numbers to all technical stacks. This can be very useful when interoperating between different technical stacks to ensure that the client is using a contract version consistent with the one the server used to implement the service. The last thing I would like to show in this video is the CLI tool called buff, which is very useful when working with protobuf contracts. It can help with linting, detecting breaking changes, and building the client libraries. Once we install the tool according to the documentation, we can initialize the buff configuration for the repository with the command buff config init. This creates a default config file where we can fine-tune several configuration parameters according to the specifics of our contract module. And then we can compile our contracts by executing the command buff build, which by default does not print any output if the build is successful. If we make a typo in one of our contracts and run the command again, we can now see a build error. Another useful command is buff lint, with which we can execute linting of our contract files, checking that our code satisfies the typical protobuf conventions. If we run buff lint, we'll see that we made a mistake in one of our type names. The return type of an RPC should have the response suffix instead of reply according to the default conventions. The linter can validate several other rules related to naming, versioning, folder and file structure, and more. And the linting rules can be granularly configured in the buff.yaml config file, where we can opt in or opt out from adhering to any of the rules. The build and lint commands are useful to include in our CI build before we generate any client libraries to ensure the correctness of our contracts. The CLI can also be used to detect breaking changes in the contract. This can be set up in our CI build to be executed on any non-main branch and compare the contracts to the main branch to detect if any of the differences introduce any breaking changes. The last feature I would like to show is the capability to generate code using various plugins. This is optional. We can always build the contracts and generate the code for our technical stacks without using any plugins, like how we did it for .NET. But using buff can make the process easier. In order to do the code generation, we need to create a buff.gen.yaml file where we can configure a set of plugins to use. For example, we can configure the following plugin to generate the libraries for Java and Python for both the protobuf models and the gRPC services. Once we created this config file, we can execute the command buff generate, and the generated code will appear in the configured output directories. These plugins can make generating library code for the various technical stacks easier and decrease the amount of explicit project setup we have to maintain in the contract repository. Although it needs the most amount of upfront work to set it up, I think this third approach, creating a dedicated repository for the contracts with its own CI build to generate and publish packages for the various technical stacks, is the best solution. It has the following benefits. Both the contracts and all the necessary setup needed for the code generation is extracted into a dedicated repository, and it is not needed to be duplicated in every service. It provides a clear approach for explicit versioning by publishing the packages for every technical stack with a consistent version number. And it provides a central place to implement extensions to the generated types, which can be utilized by all the consumers. I hope this overview provides useful information about the various options we have to maintain our gRPC contracts to be able to find a solution that fits into our infrastructure well and will make our developers happy to work with.